Hello, Internet. My name is Jansen Lee, and at present, I'm working towards getting my PhD in mechanical engineering. My work involves a lot of mechatronic systems, and pretty early on into my graduate career, I realized that if you do some searching around the internet, there's a lot of information about how motors work. However, it turns out that a lot of what's on the internet is, well, less than accurate. And it's not always easy to tell the difference between someone who actually knows what they're talking about and someone who just thinks they know what they're talking about. So this series is my attempt at providing a reliable source of information from a beginner's understanding to a more advanced understanding of how motors, more specifically permanent magnet DC motors, work and how you can operate them practically. But before we talk about how you can use or control motors, we have to back up to some underlying physics. Now, we've probably all seen and played around with magnets. However, the way they work is a little less straightforward than it might seem. Magnetic fields, which are the vector fields emitted by magnets, are actually caused by synchronized rotational motion of charged particles in the materials. Just as rotating charges cause the magnetic fields produced in permanent magnets, translating charged particles also produce magnetic fields. For instance, a wire with charges moving through it will produce a magnetic field which revolves around it in a right-handed manner. If we then coil this wire into a loop and run a current around it, the magnetic field will add constructively in the area enclosed by the loop. As shown here, a current moving counterclockwise around a loop of wire will produce a magnetic field inside of it which points out of the screen. This is known as induction, and it's exactly how things like electromagnets work. So, moving charged particles create magnetic fields. But it goes both ways. Anytime one of these charged particles moves through an existing magnetic field, there will be a force on that particle. This force is described in the second half of the equation Hendrik-Lorentz derived in 1895. Lorentz's equation says that the forces on a charged particle F are equal to QE plus the cross product of QV and B. The first term says that if a charged particle is in an electric field, it will experience a force proportional both to the electric field strength and its charge, and this force will be applied along the direction of the electric field. The second term, which is more important for us today, says that if a charged particle moves through a magnetic field, it will experience a force which is proportional to the strength of the magnetic field, the charge of the particle, and the portion of its velocity which is perpendicular to the field. This force will be applied perpendicular to both the magnetic field and the velocity of the particle. Where this force becomes practically useful with motors is when we apply it to a lot of charged particles moving through a wire. When charged particles move through a conductive material driven by some electric field, we call this a current. Current is measured in amperes, or amps for short, and it's essentially the count of the number of charges moving through a cross-section of the material per second. If we run a current through a wire, the charges in this wire can be thought of as having some velocity in the direction of the current. If this wire exists in an external magnetic field, which is not parallel to the current, each particle will then have a net force applied to it as a result. Thus, we can show that the force on such a wire in a magnetic field is equal to IL cross B, where I is the current, L is the length of the wire, and B is the magnetic field strength. Using this idea, we can now convert electrical current into mechanical motion. Now let's apply this idea to a closed loop of wire. If we have a square loop with current running around it, as shown here, and we position it in a magnetic field, the sides, which are now shown as into and out of the page, will have forces applied to them due to the magnetic field. These forces will be in opposite directions, and they will create a net torque on this loop of wire. This will rotate the wire until the two forces eventually come to rest in line with each other. Noting that torque is the cross product of distance of application with the force being applied, we can now quantify the torque on this loop of wire as the cross product of the diameter with the result of IL cross B. Now we have an equation for the torque on a current-carrying loop of wire in a magnetic field. Before we can move on to looking at how motors work in practice, we have to talk about one more physics principle: Faraday's law. What Faraday's law essentially says is that the flux, which is another way to say the magnetic field going through the closed loop, cannot change too quickly. If an external magnetic field going through the loop changes, an electromotive force, which is a fancy way of saying voltage, will be generated across the loop itself such that a current flows in it and induces a magnetic field which resists the changing magnetic flux. For example, if the external field increased in strength, a field would be induced inside the wire which points opposite the direction of the external magnetic field. In a motor, this voltage is referred to as back electromotive force, or back EMF for short, and it's fundamentally important for understanding the dynamic properties of motors. Another important thing to realize here is that changes in flux can happen due to changes in magnetic field strength, but they can also occur due to changes in orientation of the wire relative to the field. Imagine, for example, a loop of wire oriented such that a magnetic field points directly through it. Then, if either the loop or the wire rotates such that this is no longer the configuration, the magnetic field passing through the loop goes down, and thus the flux decreases. This change in flux would produce a back EMF in the coil of wire, causing a current to flow, thus generating a magnetic field. Rotational cases like this are the primary way we see back EMF generated in motors. So that concludes most of the underlying physics ideas we need to get out of the way before we can start talking about how motors work in practice. Next time we'll start this by exploring how to make motors turn for more than 180 degrees at a time.